All right, the final exam review for fall 2020, I shortened it up. It was like 50-something questions before. That file may even be in Canvas somewhere. You may run across it and see it, the original review. That's fine. You can do that if you want to. But I shortened it to like 25 questions just so it would be something we could finish. Hopefully we can finish it when you come back next week because you're going to come in here and take the test, right, in class, either at 8 or if you made another time with me. Some people, I don't remember if in here that happened, but some people have other things going on, and so I've let them come to another class or whatnot. And then we've been offered a couple of other times that I'll be available that people can come by, like the original 4 o'clock class that some of y'all might even have been in. True or false, a parameter is a numerical summary of the population, whereas a statistic is a numerical summary of the sample. What do you think? True, right? Parameter, population, sample, statistic. So B. We'll call it. We'll say this name is key. All right. So B. And if you'll notice on the back of the last page of your review, it's got the answers there. So I'll be checking them as we go to make sure we don't miss anything. You can check as you want to behind me just in case I mess up. All right. I also plan to have this copy of the review in Canvas. It's not there yet for y'all, but it'll be there later today is my goal to get it out there. A recent study attempted to estimate the proportion, and look, this is a situation, a scenario, but it's really blah, 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 and you're worried about what's going on here because it's going to ask you to identify some things. So proportion of Florida residents who are willing to spend more tax dollars on protecting Florida beaches from environmental disasters. 4,800 Florida residents were surveyed. Which of the following is the sample? So if you look at that, what's the sample? Just without reading the choices. What's the choices there? Or what's the sample? The ones who were surveyed. So who were surveyed? The 4,800 Florida residents. So the sample here is D. The sample here is D. It's the ones who were surveyed. All right. Then it says, number 3 says, refer to the previous question. Which of the following is the population used in the study? So it says, estimate the proportion of Florida what? Residents. So it's going to be what? What's the population? All Florida residents, which is B. So you see how they're just giving you a situation and saying, hey, what's the sample? What's the population? Right? They may even say, what is the number 4,800? Well, it's a statistic because it's talking about the sample, right? So you see how the thing we just did, number 1, true or false, and then plays into this. So here, classify as qualitative or quantitative. If you recall, qualitative is like a category. Quantitative, a quantity, that's a numerical value, right? That means something. So eye color, is it a quantity, a number, or is it a quality, a category? Qualitative, right? It's a category. So this is going to be B. So number 4 is B here. What about grams of sugar in a donut? Quantitative, right? That there is actually a value associated with that, right? And in donuts, it's usually way too high. That's why I like donuts so much. So, but that's A. And then what about the shape of this distribution? Is it bell-shaped, uniform, skewed, or skewed right or skewed left? Bell-shaped, right? When it has this basic kind of rise and fall, it's a bell-shaped. All right, so if it was uniform, it would look like a rectangle, like all the bars would be the same height. If it was skewed to the right, it would look like this. That's skewed right, where the tail is on the right side. Skewed left would be where the tail is on the left side, right? Correct, I should say. So, and it could be this. This thing could change shape, right? I mean, it could be pulled over here and have a tail on the right side, be skewed right. Or it could be pulled over here and have a tail on the left side, be skewed left. Or it could be straight across, same bars, same height, uniform distribution. So those are the different kinds of those distributions there. And then determine the class, determine the number of classes, in the frequency distribution. So if you look at this, how many classes are there? 5, right? I mean, literally you're saying 1, 2, 3, 4, 5. There's 5 classes. So C for number 7. Number 8 is compute the range of the data set. What is the range? It's the largest value minus the what? So a max minus min probably would have been an easier way to write that. The largest value is 20, the smallest value is 3, and that indeed is 17, right? 20 minus 3 is 17. So they may not be in order, right? But you just go and find the largest value. 20 is the largest, 3 is the smallest, and you get 17, which is A. So 7C and 8A. And then here's a bar graph. Can you read a bar graph? During which week was the fewest number of tickets sold? Week 2, right? That's the shortest bar. Week 2, D. So you can tell, I mean, you had some of these same questions on the test that we had, right? But again, because I'm trying to do as much as I can in 50 minutes, I'm trying to give you some things that are recognition. Like you see this, you do it, the number of classes, right? Things that they still test, do you know what's the terminology, what's going on, but they're quick, they're simple, they don't involve a whole lot of calculation. You know, and there are going to be some of those, but, you know, not a ton on here. So D for number 9 there. Number 10, use the frequency distribution to determine the class limits of the third class. So if we go to the third class, so this is the first one, second one, third one, right here they are. What are the limits? The lower limit is what? 9, and the upper limit is 11, right? So then for number 10, we have lower limit 9, upper limit 11, which is B. And by the way, if y'all see any typos, let me know. Sometimes there's typos in some of these, and I don't catch it. The weights in pounds of babies born at St. Mary's Hospital last month are summarized in the frequency distribution. 5 to 5.8, 5.9 to 6.7, and they have the number of babies. What is the class width? What is the class width? So how do you find class width? It's 2 what? Consecutive lower limits. We're really tempted to just subtract these 2 values, but that's not what it is. It's these 2 values, or these 2 values, or these 2 values you're subtracting. So it's going to be 5.9 minus 5.0, which is 0.9, which is D. It's the difference of 2 consecutive lower class limits. It's not an upper minus lower. So the class width there is 0.9 pounds, which is D. The median of a data set for a variable is the data value that is what? Lies in the middle when it's arranged in ascending order, right? So that's D. If we look at B, appears the most, what is that called? This is the mode, right? And then the average, the sum of all divided, that's the mean. And then this last one is the median, right? And that's what we're asked for. So then D, that's the median. So be aware, it could ask median, what is the mean, what is the mode, right? That question is set up to be any of those. So you just have to know. Appears the most is mode, the arithmetic average is mean, and then median is the one that lies in the middle. The scores from a state standardized test have a mean of 80 and a standard deviation of 10. The distribution is roughly bell-shaped. Use the empirical rule to find the percentage of scores that lie between 60 and 80. So we have this bell shape, right? What is the mean right here in the middle? It's 80, right? And then we want to go out here to 60, so we go 70, 60. Why did I draw it that way? Because the standard deviation is how much? 10. So that's how many standard deviations away from the mean? 2. So if we go 2 standard deviations this way, this is how much percent? It's 95% in all of that, right? But we don't want all of it. We only want this piece over here, and that's how much of that? How does this shaded part compare to all that? It's half of it, right? It's symmetric, it's half of it. So if we go if we go 1 standard deviation on each side, it's 68%, then it's 95%, and then it's 99.7%. That's the empirical rule. So if 2 standard deviations is 95%, this is half of that, which is 47.5%. Half of that's 47.5%, which is D. So 12 and 13 are both D. That was 11. Remember the 68, 95, 99.7 rule, that's the empirical rule. So there's going to be a question that gives you the mean and the standard deviation, and it's going to go so many standard deviations on one side or the other of the mean. So you take whatever the 68 to 95, 99.7 and then half it. Or it could be both directions, or it could be 1 standard deviation this way and 2 this way. We'll take half the 2 and half the 1 and add them together. Right, so that's what it's going to try to get you to do, some sort of combination of the empirical rule there. If the graph is symmetric, what is the best measure of central tendency if it's symmetric? If it's symmetric, the mean. If it's symmetric, the mean. If it's skewed one way or the other, it's median. So think about income. Income is something that has a cap at 0, right? And a whole lot more people make closer to 0 than they do $1 million a year, right? But there are people, even here in Oxford, right? You got an SEC football coach that lives in Oxford. They make a lot of money. You got doctors and lawyers that make a lot more money than I make teaching. And maybe than you'll make doing whatever you do. But you got a whole bunch of people who probably make between $20,000 and $120,000. A whole bunch of people. And then you got a few people making less and a whole bunch, a few people making more. So the few people making more skew it way out to this side. If you just took the average salary in Oxford, that SEC coach would make it look like we made a lot more money than we did just from their $3 or $4 million a year, whatever they make. Right? That would bring the mean up. But if you took the median where you just put them in order and took the one halfway in the middle, that's a better representation of a skewed data set. But the mean is better whenever it's symmetric. So mean symmetric, median skewed, right? And then same thing on dispersion. Standard deviation is better on symmetric. And then the, what do they call it? The quartiles, the 5-box plot, the 5-number summary is better for the skewed. Couldn't think of what it was called for a second. Find the z-score for 50 when the mean is 52 and the standard deviation is 6. So here's my x, here's my mu, and here's my sigma. So x, let's see, z equals x minus mu over sigma. And if you want to say it was x bar and s, if it's a sample, I don't think it tells us here whether it's a sample or parameter, or population. So the z-score is going to be what? $50 minus 52 over what? 6. So negative 2/6 is negative 0.33. And it repeats forever, but we can tell it goes to 2 decimal places here. So then 15 is also D. That was 11, 12, 13, 14, and 15 all D. So you got to remember x minus mu over sigma. The value minus the mean over the standard deviation gives you the z-score. A card is drawn from a standard deck of 52 cards. Find the probability that the card is a queen or a club. So the probability that the card is a queen or the probability that the card is a club. That's terrible. That's not really a club. Let's try that again. So this is going to be the probability that it's a queen plus the probability that it's a what? A club minus the probability that it's what? A queen and a club. So how many queens are there in a 52 card deck? 4. So there's 4 out of 52 for the queens, plus how many clubs are there? Right, there's 4 sets of four suits of 13 cards. Right, 13 times 4 is 52. So you got 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And then how many are queen and club? So is there any card that's both a queen and a club? There's one card that is the queen of clubs, right? And I'll try to remember to have that. In fact, let me just go to it real quick while we're talking about this. I'll have this printed for you along with anything you need, the table 5 and all that stuff. All right. This will be printed for you and I'll give it to you. So here, you got 13 spades. You got spades across the top, hearts, then clubs, and then diamonds. So there's 13 of each. How many queens are there? There's 4, the next to last column on the right. And then third row, next to last column, there's 1 queen that is queen of clubs. So here, this is minus 1 out of 52. So you have 4 plus 13 is how much? 17 minus 1 is, so you got 16 out of 52, but wait a minute. You don't want to leave it 16 out of 52 because they're both even, so at least a 2 does, and maybe something more. So as you simplify that, you go 8 to 26, or you can even go further and say, oh, wait a minute, they're still even 4 out of what? 13, and you can't go any further. So 4 out of 13, which is not D this time, right? We had a bunch of D's in a row. But B, 16 is 4 out of 13. So you have to know that something or something else is the sum of the 2 probabilities individually minus the probability that they both happen at the same time, which in this case can happen. Sometimes it cannot happen. They can't both be something, but here they can both be a queen. Or like if you said a queen or a 6, you don't have a 6 and a queen on the same card, but you do have a queen of clubs on the same card, queen and club. Use the spinner. Assume equally probable that the pointer is any of the 1-5 number spaces. Find the probability the arrow will land on 3 or 1. So how many choices is 3 or 1? That's 2 choices out of how many? 5. So this is going to be 2/5, which is B for number 17, right? Oh, and I didn't bring my calculator. Does anybody have the calculator? One of the calculators with you? Any calculator at all? I wonder if there's one in here. I meant to bring it for this problem. Or for some of these, there's not one of these in here that does this. So then, on number 18, we have the permutation of 10p6. You can actually punch it in the calculator. There are a few calculators you can check out in the library. The TI 30XI plus multi-view is in there. There are some Casios that they give you for stats. They're not as easy to use. I would try to get the multi-view if that's the one you get. And under the stats menu, or either see the stats, vars, or data, it's got the P, the C, and the factorial. And literally you hit 10, you go to the menu, get the NPR, and then hit 6 and then hit enter, and it gives you the value. All right, it gives you the value here. So let's see if we multiply this together. Let me just multiply something together real quick on my phone and see. That's not. Oh. Is that what it is? All right, so what is the formula for the permutation? Y'all remember that? I mean, you're gonna plug it in. It's 10 factorial over, I think it's 10 factorial over 10 minus 6 factorial, I believe is what it is. So let's see if that's what 10 times 9 times 8 times 7 times 6 times 5. Yeah. So this becomes 10 factorial over 4 factorial. This is what the calculator is doing. So then you have 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. Those divide out. So 10 times 9 times 8 times 7 times 6 times 5 is 151,200, and B is what it is here. All right. I did mean to have the calculator because you just punch it in, really. So I will. Oh, and let me say this about checking out a calculator for final exams. If you checked one out in the semester, they only ask for your ID because it's the middle of the semester. They can send me a message and say, hey, can you tell so-and-so to return their calculator? But exam week, you're leaving for the winter, and this time it's a lot longer. So they're going to ask for either your keys or your cell phone along with your ID because they don't want you to go anywhere with the calculator. Okay, they want to get it back. And we only have like 6 of the ones I'm talking about in there. So they don't want them to walk off. They need to keep them so that somebody else can use them if they need to. So you can use one and check it out, but there won't be enough for everybody. So if you have one, bring it. But if you don't, then you can check one out. But just know they're going to ask you for something more than just your ID. ID and keys or ID and cell phone. All right, so here, number 19, this goes back to the empirical rule. Approximately blank % of the area under the normal curve is between mu minus 2 sigma and mu plus 2 sigma. This coefficient tells you this is 2 standard deviations, okay? So if you recall the curve here, right? You got 1, 2, 1, 2. So this was 95%. One of them, 68%. What was 3 of them? 99.7%, okay? So this coefficient is going to change. It's either going to be sigma, 2 sigma, or 3 sigma. Sigma is going to be 68%, 2 sigma is going to be 95, 3 sigma is going to be 99.7. So this is, on this one, 95%, which is D for number 19. So we're back to D. And then the highest point on the graph of a normal density curve is located where? So here's your normal density curve. This is normal, right? The bell-shaped. What's this highest point going to be out of these choices? So it's going to be what now? I mean, yeah, but as far as just in general, not necessarily it's going to be the mean, right? So remember the inflection point. The inflection point is where there's 1 standard deviation away. Okay, that's where the inflection changes. And inflection, remember, was going from like frowning to smiling, or the other way around. So that's where it changes. So, but the mean, and then those are just plus sigmas to the right or whatever to the left. So B. So the mean is the highest point of the normal density curve, the mean. And if you recall, being symmetric, it's also the median and the mode. The mean, the median, and the mode are all there in the center of a normal one, of a symmetric one. So here you have a normal curve, and it says, tell me what mu and sigma are. So you have it. What is mu? Mu is the thing in the center. What is mu? -6, right? And then what is sigma? Well, how do I know what sigma is? Well, it shows me 1 standard deviation over, and how far apart are these? Or how far apart are these? They're 2 apart, right? I mean, you can do the subtraction, -6 minus a -4 or whatever, but it's 2 units apart. Or -4 minus -6, I should say. Larger minus the smaller. But mu is -6, sigma is 2, so which choice is that? Is that this one? A. All right, so here's the other thing I'm going to give you is this table. I put it on here. I didn't put the picture of the cards on there. I forgot to do that. But here I'm going to give you this table, a printout of the table along with a printout of the cards and the dice, so you have that with you. That way you can look up anything you need to look up along the way. So this is the first time we've had to look this up. And I drew this line in here because if you notice I jumped from negative 1.5 to 2.0 because I'm trying to give you what you need here. If I put the whole thing on here, you couldn't read it. It'd be too small. So find the area between negative 1.5 and 2.5. So when I draw my picture, here's the mean, right? Negative 1.5 is probably right here, and 2.5 is probably way out here. So I want to find all of this area in here, right? So if you recall, when I look it up on our table and our book, remember, different books can be different. When I was tutoring over at Ole Miss a couple years ago, in their book that I was using that day with that student, and it was actually I tutored about 4 or 5 students in stats, and all of them had the same book, and it went from the z-score back to the mean. So they had to know that if it was all the way left, they had to add the 50% back, or they had to take it away from 50%. They had to figure out what to do with it. Ours is everything less than that value. So if I look up 2.5, I get everything from here all the way back forever. So let's look up 2.5. Here it is. And it's this first one is 0.0. 2.509938. So this value here is 0.9938. But I don't want everything. I want to take this stuff over here away from this part over, right? So then if I look up the z-score for this, it gives me everything to the left of negative 1.5. So if I look that up, where's negative 1.5? Here it is. So 0.0668 is that value. So how do I find my shaded region? I subtract, right? The 2.5 proportion minus the negative 1.5 proportion. So 0.9938 minus 0.0668. So is that 0.0270? Some of y'all have a calculator and can do that maybe. Is that right? 10, did I do that wrong? Did I borrow the wrong thing? Is that one of the choices? That's not one of the choices, is it? So that can't be right. Between 2.5. Oh, that's not 0. That's 9. Is that right now? 9270. And that's A. Is A the answer? Yes. All right. Yeah, I did 9 minus 0 and got 0. That doesn't work. That's not in anybody's math. That's made up stuff. So 92.7% fall between 2.5 above and 1.5 standard deviations below. So here, again, I gave you a snippet of the table. X is normally distributed. The mean is mu is 80. Standard deviation is 12. Find the probability that X is less than 95. So what I need to do is I need to convert this to a z-score. I need to get a z-score for this. So I need to do z equals x minus mu over sigma. What is my x here? 95, right? This is my x. And then minus, 80 over 12. That's 15 over 12, which is 1.25, isn't it? Everybody do that and get 1.25? So then, if that's 1.25, then I'm looking at 1.25. So here's 1.2, and I got to go over here to 0.5, right? I got to go where they meet up. So it's this number right here, right? 1.25, so 0.8944. So this is going to be the probability that Z is less than 1.25 is 0.8944. Because remember, our probability table gives us less than. And let me go back a page to show you. It has this up here, and it shows the area to the left of that z-score, right? That's on the table itself. I don't have it on the next page, but that's what's there. So that's what's happening here. It's that number, so it's 0.8944, which is A again, right? So 23 is A. And then the last two, I tried to give you something you could recognize again quickly that wouldn't take a ton of time. You have the null and alternative hypotheses, determine if it's left-tailed, right-tailed, or two-tailed, and then what is the parameter being tested. So if I look at 24, H naught is mu is 9.8. H1 is mu is not equal to 9.8. So first of all, is that left-tailed, right-tailed, or two-tailed? Two-tailed. Not equal to, it could be greater or it could be less. That's how we know it's two-tailed, right? And then what's being measured here? Mu. So it's either going to be B or C. It's going to be C because it says mu right here, right? It can't be that one. So C, it's two-tailed and measures mu. All right, 25, H naught, sigma is 8. H sub 1, or the alternative hypothesis, is sigma, is less than 8. So is that right-tailed, left-tailed, or two-tailed? Left-tailed. Left stands to the left. It's left-tailed, so it's got to be B or C. And what is it measuring? So we know it's not these two. It's measuring sigma, so it can't be that one, so it's what? C again. All right? It's C again. So remember, we have to be here next week for the in-class portion of the final, and hopefully you can finish it and won't have to put anything online. All right? Thank y'all.